Okay, folks, I just have a little note that I want to get in that that really doesn't have, I don't think it has any homework associated with it, but it is an important little thing to discuss. And right on cue. Beautiful.
Hello.
Hello.
Is Miranda here?
Yep. So this little note is a discussion on how we practically actually measure a rate in an experiment. And you've already had an example of one. We just did one here. Because the reaction produced a gas, we could collect that gas and we can then measure how quickly the gas is produced. In your lab, you're going to be asked to use the ideal gas law. Actually, we tell you the factor, so it's not like you've got to really use PV equals nRT, but we can use PV equals nRT to determine, right, what the number of moles was that was produced from the volume that we obtained. So measuring the volume of a gas is one way we can practically measure how quickly the reaction is going. That's what we want to talk about right here just briefly. What other factors can we measure? What other things can we measure? So actually measuring rates of reaction. Hold on one second. I don't think we need this information. There are many properties in which chemists can measure to determine the reaction rates. The method chosen depends on the nature of the substance involved and the type of reaction. So it depends on what kind of products and reactants we're dealing with. Ideally, the measurements must be made without disturbing the progress of the reaction. That is an important concept, but it's not important for you to memorize. But you don't want something that then has an effect on the reaction itself. So it's got to be something that you can observe from afar that doesn't change the rate of reaction itself. Okay, so here are some things that we can observe, and for the sake of me testing you, like in a multiple choice question, I'm giving you some examples of some colors, and I do want you to know those, right? The classic, do we have to know the colors for that thing? Yeah, because in order for me to test you on a question, I need you to be aware of those colors. There are many other situations that we could have, but these are just some examples, some prime examples that come up quite a bit. So if a substance is one color as a reactant and the color changes as a product, then you can obviously use the change in color. You might ask, how do we actually measure color? Well, we use something called a spectrometer. Once you're done writing, I'll talk about what a spectrometer is. So essentially what chemists can do using a spectrometer is to take a sample, all right, of this particular reaction, get it ready to go, perhaps have the purple permanganate ion in a container. And the container they use is a very specialized container. It has a very specialized dimensions because it has to have certain dimensions to fit into the machine. Also, you can't change the depth of the liquid in which the light goes through, because that will then change how much light is absorbed. So you've got these very specified dimensions in the machinery. And what they'll do is they'll take a very bright light and they'll shine that light through the substance. And the light that comes out the back end will obviously be colored depending on what the color of the substance is. So if the substance in there is a color like that, then the light that comes through is the color of that thing. It's been imparted to it, all right? Because it's absorbed some of the light. And then what they'll do is they'll send that through a prism or a diffraction grating, and that color will get spread out into its spectrum, and there'll be certain lines in that spectrum, all right? And then when they have the chemical reaction take place, then the color of the chemicals changes and the color of the spectrum changes. And so they can then measure how much of each of the two chemicals are. So as the reaction happens and it might go to a different color, then the different color starts to appear in the spectrum. The first color starts to disappear, the second color starts to grow, and if they notice how the original color dies down and the second color grows, they can actually measure that with respect to time. So they can initiate the reaction and observe as one color disappears and the other color grows. And computer sensors are doing all of this. They would have some kind of a camera on the back end, kind of like a digital camera, collecting the spectrum, sending that data to a computer, and then the computer can measure how that spectrum is changing and how the color is changing. And they can create a nice graph of the reactants and products changing, all right? So they can definitely do that very quantitatively, all right? So you can measure color quantitatively. Computers and cameras and various other sensing machinery can easily do it. Who else just came in the door? Oh, they haven't come back yet. Oh, they're wandering. Excellent. Yes. Another observable that we can measure very easily is the pH. If you have a chemical reaction that produces H pluses or OHs, then the pH of that solution will change. Perhaps you start with something that's acidic and it absorbs those H pluses and turns into something that's neutral, then the pH will change. We haven't used the pH meters. Did we use the pH meters last year? No, but we will be doing experiments where we will be measuring with pH meters. We're not going to do a time relationship. We're going to be adding some base and seeing what the new pH is, but we can do time relationships. We could put the pH meter into the solution, bring in the other reactant, start the computer sensor, have it measure the pH as it changes with time, and we will get a nice curve, just like the curve you're going to see and just like the curves that we saw in our little examples yesterday. So pH is very, very easy to measure with a pH probe or a pH meter. Electrical conductivity. A solution, if you recall, is an electrolyte if it has ions in it. And an electrolyte can conduct electricity. If a chemical reaction either produces ions, more ions in the products than in the reactants, then it will be able to conduct more electricity. If a chemical reaction brings ions together, which then locks them away, say in a compound, and the number of ions decreases, then the electrical conductivity decreases. All right? An electrical conductivity apparatus is a very simple apparatus. In some kind of an encased probe, all right, there will be a couple of wires, and I'd be able to draw this better, but my cart was bumped. And those wires would be connected to two electrodes that are a certain distance away, and all you'd have to do is put that particular electrode into a solution, again, connecting those wires to the computer, and as it attempts to send some current between those two electrodes, because the computer can put a little voltage on it, try to push some electricity through it, as it measures the current flow, it will then get a measurement of the conductivity. If the ion levels disappear, then the conductivity, gets lower and lower and lower, and if the ion levels increase, then the conductivity increases, right? And again, this can all be done with computer, okay? All right. And here's the one that we looked at today. Pressure, change in volume of a gas, or it could have been a change in pressure. Pressure is a tricky one to do. Because pressure can slow a reaction down depending on what the type of reaction is. We'll talk about that when we get to the equilibrium unit. Mr. Edgar is always trying to find ways to make labs in the biology class more quantitative so that you have numbers that you can deal with. That's the nice thing about the physics and the chemistry. And I know you guys do a reaction, I think you just might have completed it, where you're talking about the enzyme action and generating, it's a decomposition of hydrogen peroxide, I believe. So you have bubbles coming off the hydrogen peroxide. We've tried to fiddle with that and try to come up with a way in which you could maybe do it like this, where you're catching the hydrogen peroxide and then measuring the rate, right? Because I think something like heat affects your enzyme action or something, right? So then you could do one experiment hotter than the other, do another experiment with a different pH than another, et cetera, et cetera. We've had varying degrees of success trying to get it quantitative. It doesn't always work out in that you got potato in there and all kinds. Is it potato? Is it the potato one? Yeah, look at there. I got a response out of you. That's good stuff. I know you guys love that potato lab. So we've tried to make it quantitative. And this is what this would be a great one to measure for that because it's producing oxygen gas. So you could get a measurement of the rate. The problem is you'd need to know this lesson so that you could draw the line and then take the slope so you get the rate. Then you're going to be comparing those slopes for different temperatures, right? And as soon as I explained to him that that's what would need to be done, he's like, well, no, that's way too, I don't know, that's a lot of graphs. Anyway, that would be the ideal way to do that experiment, right? Is to collect a bunch of gases at various temperatures and various things and then go from there. Okay, so just a couple of examples here. Actually, I'll just do the one example. So here I've got a chemical reaction that is taking place. Some bromine liquid in with some, this looks like, this is called formic acid. It doesn't matter. You don't have to worry about that. And what could we use? What kind of changes? Change in, what could we be looking for? You give me an example and you tell me why. What could we be measuring out of the ones that I've told you about in the last few moments? Yep, Shauna?
The change in color?
Yeah, we could use a change in color. What would that change in color be? What would we observe? To colorless, the brown to colorless, right? Because of the bromine. Yeah, excellent. Brown to colorless, excellent. So we could use that bromine molecule to bromide ions. Another example? That's correct, yep. Change in pH, and why is that? Why could you say it? Yeah, there are no H plus ions free to move on this side, and there are H plus ions free to move on this. So change in pH, all right? We can observe that there is H plus in the products, right? What's that going to do to the pH as time goes on? If H pluses are being formed, what's going to happen to the pH as time proceeds? Yep, sir? It's going to get lower because it's going to have more H pluses, which is more acidic, which is a low pH, and therefore the pH should be declining. That makes sense, everybody? So if we had a pH probe, we could measure how that pH was declining. What else could we measure on this one? Actually, I picked this because we can talk about a lot of stuff in this one. What else could we measure in this one? Yeah, Shauna?
The electrical conductivity.
The conductivity, yeah. So, conductivity, I'm just going to put that there. C-O-N-D, you can get it. And why can we measure the conductivity? Why is that measurable in this case? Yep. Yeah, there's more ions in the products. They may be oppositely charged and they may balance each other out, but there's no ions in the reactant. It shouldn't be conductive. And there are ions in the product that will be conductive. So there are ions formed, more ions in the products, and therefore the conductivity should increase with time. It should go up as the reaction goes. And again, it would go up quickly at the beginning, and then it would level off to a maximum conductivity at the end. It would look just like our graphs. But we've got everything covered except what? What's the only one we haven't talked about? The volume. Can we do a volume? Have we got a gas being produced? Yeah, we do. We've got carbon dioxide gas being produced. We could have collected the carbon dioxide gas. All right? So we could measure the change in volume of the gas. CO2 gas is the only gas produced in products. All right? So the volume of that gas would increase, and we could have measured that. Okay? To practically do that lab, they don't let us have bromine liquid. It's fairly dangerous stuff. Okay? All right. And we're not going to bother that. And that's that. That's the end of that one. And like I said, there's no homework